So after our item analysis, we did post the reconciliation for the Module 2 assessment first attempt. And what we did was highlight some things. There's a link to the item analysis, so you don't have to dig it out of the resources folder, but it's still in there. So if you go into videos and then go into fall, there's the item analysis for the Module 2, but that same link will get you where you need to go right here. Same thing. You know, you don't have to use the words verbatim when you're typing out your answers and the words of the question. So you don't have to type verbatim the exact words of the question. And this is something that I would like to encourage you to consider. When you're reconciling, it might be better if you paraphrase the words of the question, because you're putting it in your own words. And that means that the question that's a challenge is going to stick better in your brain. That's called deep processing. It's part of tactics for thinking. And it has to do with getting better use of your brain in a classroom environment. It's called metacognition. And for your own edification, metacognition is the study of the thought process in humans. And it's actually a formal discipline. You can pursue advanced degrees in cognitive theory and a whole variety of related topics, right? So in the fields of psychology and so on. So psychologists are keenly interested in efficient learning and how to optimize learning. So the reason that we perform the reconciliation the way we do is because there are dramatic, notable differences in the performance the next time around. For those of you that miss the assessment deadline, you can still reconcile your first and final attempt of the module assessment. And we'll be putting that out on Module 2 over the weekend, but not before the weekend. Are there any questions? Today's goal is to start to move closer to the best part of hands-on for this class. So after your first round of digital creation, your solution in Module 2, we're going to ask you to take it up a level so that you basically do more with a broader range of logic gates. And so you're going to be working with 3 or 4 logic gates in combination, and you'll be using exotic new ones that have changed life as we know it. So the NOR and the NAND have a lot to do with digital memory. So the memory components of a computer, when you have a solid state hard drive, those components are built out of NANDs or NORs, depending on the context, right? XOR has to do with encryption. XNOR and XNOR have to do with encryption. MUX and DMUX, that has to do with multiplexing. That's a $64,000 word that means multiplexing. And MUX is the short version of that $64,000 word. When you demultiplex, that's called a DMUX. MUX is what allows us to communicate. It's the switch mechanism that allows us to route traffic in a certain manner based on inputs. And well, we'll get into that more in a minute. But the thing is that I want you to be able to take your understanding of things to another level of complexity. That's the primary goal of Module 3. So we want to do the same kind of thing. Now, why am I telling you this? When you get your scores back from Module 2 for the solution, if you have to correct anything, you need to do that before you start working in Module 3. Let me say that again. When you get the scores for credit this weekend on the solution, because I'm going to go ahead and if people didn't submit at this point, I'm just going to post zeros. All right, we're not going to hold off on the scoring and return of these. So if you haven't caught up yet, and you're still trying to get something on the board, get it on the board, like today, tomorrow by noon, because by the time we get to class on Monday, what we'll do is we'll post initial credit for the module 2 assignments and solution. Everything else we've done to date, right? Now, you have to have that solid before you go into module 3. So this is like, okay, you have to be good at riding a bike with the training wheels before we let you ride on a bike without what? The training wheels, yes, okay. So that's the interest here. As soon as we clear module 3, then we get into the really cool stuff. We actually get into the digital components and the computer architecture proper. So what we're saying is we can go into something like this, and in device manager, everybody can see my screen, yes? Mm-hmm. Let me get this out of the way. We can see that, yeah? So this is the device manager and the Windows operating system. And as soon as we hit module 4, we graduated from bicycles to motorcycles, right? So that's when we start talking about all of the digital components, the physical digital components in modern computer systems. Module 5 is how those systems, the architecture of those systems in terms of the data bus and the motherboards and all that, how we put all those together. And then module 6 is about special topics, right? So multiprocessor environments, multi-threading, GPUs, you know, the gaming cards, the video cards that some of you purchase for graphics superiority in your multiplayer first-person online games. Does anybody know what I'm talking about? Anybody here have a PlayStation or an Xbox? Anyone? Yeah. Okay, those have specialized graphics processors, right? So the display adapters, they have more than just the built-in stuff. Right here you see the built-in graphics processor that's embedded inside the CPU chip. So once we shift a gear into modules 4, 5, and 6, we're dealing with the hardware pieces in computer systems. And it's fascinating stuff. But the pace is going to pick up, and the amount of content we have to cover starts to increase. So there's more content, and there's less grind with the design and that aspect of it. So if you're struggling, why am I telling you this? If you're struggling right now with the logic gate builds, rejoice. Because after module 3, the sky is clear, it dries up, the sun comes out, and then we get into the wonderful world of computer hardware and computer systems, okay? Everybody with me? All right, so what I'd like to do now is basically open up a version of the study guide. So inside your study guide, we talk about here the learning objectives, right? You're going to be doing some more reading, and you'll go back and do some more reading in the same place in the textbook. Now, I know this seems kind of redundant, but when you go back after having endured module 2, if you read our textbook sections again, more of this will click. It'll start to make more sense, okay? So it's an iterative approach. Any questions before we get into this? So inside here, we're going to go into the references. And what you should see is module 3, study guide revision 1C. And there's just a refresher on canonicals. So the canonical summary is just another way to review the canonical interest, and that's a separate resource, right? And there's actually a folder there for the canonicals. Let's review. Let me see if I have this right. Can everybody see the screen? So I'm going to beg you, and I said this before, go back and read the textbook. Well, there it is in highlights, right? So why am I asking you to do that again? If you read it some weeks ago and you're like, I don't know what the heck he's saying. If you go back and take another fresh look at it, it's amazing how good you feel when some of it clicks and you're like, oh, okay, I know some of this now, right? I got it. So we want you to be able to work with greater efficiency or facility, translating from a logic statement in pseudocode. We want you to be able to take that and derive a drawing. We want you to take a drawing and derive the logic statement. That's one of the skills that we're going to develop and refine in this module with more practice, right? So the first baby steps that you took in module 2, we're going to repeat. We're going to rinse and repeat. That's what we're going to do. And we're also going to take a view, a diagram, and go from there to the truth table, from the truth table to the canonicals, from the canonicals to the logic, and back and forward. You want to be able to work up or back, down or up through that process, either way, with the information provided. So why is that important? You might be in a job sometime soon where somebody says, hey, there's a simple piece of software we need to automate some things. Is anyone familiar with a theme park? Has anyone here ever seen a Jurassic Park movie? Has anyone here ever seen the original Jurassic Park movie?
Yes. Yes.
Okay. In the original Jurassic Park movie, do you recall that the whole park was automated?
Yeah.
That from a single screen, you could what? You could turn on or turn off lights. You could open or close gates. You could do a whole variety of things. We're talking about ones and zeros. The same thing that you're doing here, right? So what I'm telling you is that if you understand how this logic works, you can design a chip that basically makes sure that the roller coaster in the theme park doesn't kill anyone. You could call it a safety module. Does everybody understand what I'm saying here? All right, so what we're going to do now is take a deeper dive on this. So one of the first things we want you to understand is the concept of an electric circuit. So one of the topics that we're going to engage here it starts to get into the physical realm. It has to get into the electricity piece of this. Because ultimately, the hardware that you use is electric, yes? You don't have batteries. What good is this if you don't have a working battery, right? If you don't have juice, if you don't have current flowing. And we want to understand a little bit more about electric current and what it does and why it's so different with semiconductors. Now, everybody knows what a conductor is, right? Has anyone here had basic physical science? The periodic chart. You have the metals on the periodic chart. The periodic chart gives you elements of the metals, and those conduct electricity, they conduct heat. Everybody knows what I'm talking about, right?
Yeah.
Then you have insulators on the other side of the chart, the periodic chart. So you have like silicon, ceramics, plastics, carbon. You have all those wonderful things that insulate from electricity, right? And what we want to do is take a moment and think about the way electrons work. When the circuit is closed, here's a basic battery. When the circuit is closed, the light is on, and there's a switch involved. The thing that I want to call your attention to, and this is a nice way to end a long week. This is lighter stuff. It's intuitive stuff, but it's important stuff. Because if you don't get this stuff, you're going to be frustrated working with computer hardware the rest of your life. These are electrical animals. Digital components by nature are electrical creatures. And the more you understand about how electricity commands them or how they yoke the electricity, right? Has anyone ever heard the phrase, you rule this or it rules you? Something like that. Have you ever heard a comment like that?
Yeah.
Yeah. You got to get a hold of this because you're either going to be the boss of this or it's going to be the boss of you. Right? So now you can get philosophical with that comment all you want, but the point is that electricity is central to this. When a circuit is open, when the switch is open, what you see here on the right-hand side, I want you to understand the diagram and what it means. So here is A and B, and there are two switches, one after another. We call that a series of switches. It's serial. It's in series. We have one after another. If A is closed, if I close A right here, do I have a closed circuit completely, or is it still open? It's not a trick question. Do I have a volunteer to answer that question?
Could you repeat what you said real quick?
The question was, hang on just a moment. The question was, in this diagram on the right-hand side, does everybody see my pointer right now?
Yes.
I have what's called this is the graphical representation of what we would call a switch, like a light switch, an on-off switch. And what you see is switch A and switch B. They're both open. Now, if I close switch A, do I have this on the left, a closed circuit, or this on the right, an open circuit?
You still have an open circuit.
Say again?
You still have an open circuit.
You still have an open circuit. Does everyone see why that's the case? If we close the gap here, we still have a gap there. And instead of showing a battery image here and a light bulb image here, we have the diagram object. This is the object we use in diagrams to depict a power supply with a plus and a minus in a circle and the light bulb. Now, you may have seen other electronic diagrams, and you're going to become really good at discerning some of those electronic diagrams. And what you have here is a light bulb, right? So a light bulb is usually, it has a filament and there's some level of resistance to the flow of electricity, which is why there's a crisscross. It's like, okay, the electricity gets through, but it's not a straight shot all the way across. The reason the filament glows is because there's resistance to the flow of electricity that creates heat. It lights up the filament because the filament is hot. Does everybody understand what I'm saying here?
Yeah.
Yeah. So that's one reason why. Now, I don't know, there could be more to that, and there are probably electronics professors in like Ivy League schools that would say, no, you don't have it right. The origins of that symbol is, yeah, all right, well, there's lots of different symbols for different components. Let's take a look at, this is a series. So when switches are arranged in a series, they act like an and. What we're looking at here is an and. Look at the truth table for this circuit. Can everybody see the truth table? A, B, out. A can be off, B can be off, the light is out. A can be off, B can be on, the light is off. A can be closed and on, B can be off, and the light is still off. What do I have now? A is closed, B is closed, boom, I have a light, okay? Now, I want you to think about that. A logic gate in the physical world, not in the abstract world, right? We've been dealing with diagrams. We've been dealing with the logical behavior, right? the abstract behavior. In the physical world, this is a physical representation of what works like a 2-input AND. The thing I want you to understand is that the switches are in series. It's one after another. We call that a serial configuration. Okay, so when you see one after another, series. Now let's look at the bottom. This is a little different. So let's take the same line of reasoning. I have a circuit. I have wire, I have a battery, and I have a light bulb. But in this case, I have a single wire that goes through the battery, through the light bulb, but with the first switch, it forks off. The wire is split. It's connected. It forks. And I have a B here, and then I have a second wire that comes up, and I have an A switch here. And what you have is an A switch and a B switch that are parallel, not serial. The A switch and the B switch are said to be configured in a parallel manner, right? So here's my question to you. Same question. If I close A and fix the gap for A and close the switch for A, do I have a closed circuit or an open circuit?
Closed.
I have a closed circuit, which means the light bulb is what? The light bulb is on. The current is flowing. I have a 1. I have electricity. Electricity is flowing, it's a 1. Everybody get that? Okay, now what happens if A is open and B is closed? What's the state of the light bulb? It's on. Yeah. What if both are closed?
It's on.
It's on. Yeah. What if both are open?
So
It's off. What we have is the equivalent, the physical equivalent of what logic gate you already know.
An
I
OR?
mean, it says right there.
Yeah.
We're talking about the OR. We're not trying to trick you. This is the same as a 2-input OR. Does everybody see what we're getting at here? Okay, series and parallel OR. We're talking about the physical wires, right? And those physical wires are really important to understand because when we're talking about building actual logic gates, physical logic gates, we're starting to deal with the physical realm, okay? Now, here's something that I want to do that may help with some wrinkles that were caused in module 2. So if you were left with head scratchers in module 2 and you're like, okay, I'm looking at these diagrams and I didn't draw a diagram like this, but where are we getting this information? This is color coded, right? So I have a 3-input AND here. Can everybody see what I'm talking about here?
Mm-hmm.
I have the Boolean function that's stated, I have an AND that has A, B, and C. And that's what it is. And so there's an AND inside here that has to be done first. So when we're working with multiple parentheses, you want to start inside those and work out, right? So I have an AND with A and B, and I want you to notice this thing right here. This is not very intuitive, but what is that punctuation right here?
Comma.
It's a comma. It's designed to set off this whole part. So this whole part is one input of an AND. And the C is the other input for the AND. Does everybody remember our other study guide? Yes, no, maybe?
Yeah.
Our other study guide. Oh, not that one. This one. This study guide. Let's see, this one. Everybody remember this business right here? Right here? Okay.
Yes.
That is this. What we just covered right here. This Boolean function is literally this diagram. Okay. What we want to do is get you used to seeing either form of the operation, whether it's in software and it's written as a Boolean function, or it's written, or it's diagrammed and it's constructed physically with logic gates. So we have an and, the A and B input happens first. We could call this W1, couldn't we? Couldn't we call this wire right here W1? Everybody?
Yeah.
And so that's W1. This is W1. This part of it right here is W1. And then the C comes in on the bottom. So the output that results from AND of A and B is W1. It's combined with C in a second and that's what this is all about. So we color coded that just so it would be a little easier to see and walk through. Are there any questions? Does anyone have any comments or observations or questions based on what we just shared with you? So let's talk about basic transistors. Has anyone ever heard of the basic transistor before? A basic transistor?
Yeah, just a little bit.
So back in the day, transistors were small objects that had wires and they were soldered onto what was called a breadboard. Okay. And what you're seeing now more are diagrams of those transistors, the schematic diagrams of transistors, but this is actually a physical transistor. So your grandparents, or actually more accurately, your great-grandparents, perhaps your great-great-grandparents, they were the first users of something called an AM pocket radio. Now, when I was growing up, it was a thing to order. It was called mail order. You'd save up, and sometimes you'd save up like shopping stamps, like S&H green stamps, right? So you go to the store, and if you bought so much groceries, you got these stamps that you could. It's kind of like the box tops of cereals. You could take 47 Cheerios box tops and mail them in to get a doll or a fishing kit, right? Or a tent. They had all sorts of programs. This was sort of like an incentive back in the day. The point I'm trying to make is that one of the prized possessions back then was having a battery operated portable handheld AM radio. And if you crack the thing open because you dropped it, what you saw were dozens of these little things. And the crystal oscillates, goes back and forth. It's the tick-tock, it's the tick-tock, it's the tick-tock of the device that makes the device work. So you have a timing mechanism. Does anybody know what a metronome is? Yeah. Okay, so metronome. Anyone ever seen these? A metronome. And the hand of, what does this hand do? Does anybody know? Has anyone ever seen it working?
It swings back and forth.
It swings back and forth like a clock. It oscillates. When you see that swing back and forth, that's oscillating. Now, I know I'm being very intentional about this explanation, but the point is that swinging back and forth, that's called oscillation. And if you're talking about basic transistors, one of the things you have to have in order to get an electronic device to work properly is this timing component, right? So as we start looking at logic gates, what we're going to think about are ways to control the timing and the switching. Okay, this is intentional. The timing and the switching, we get back to this all over again. Oh, come on. The timing and the switching of these gates. I want you to think of a switch as a gate. Logic gates. Gates are switches. This actually looks like the gate of a fence in your front yard. Everybody get what I'm talking about? Right? So we have two gates in series. We have two gates in parallel. Those are switches, on-off switches. The timing and the execution of those switches is physically what makes electronic devices possible. And more to the point, if you miniaturize these and you get them down into a very small place and you increase the number of inputs, so you have more than just 2, but you have 8 bits, 16 bits, 32-bit. Have you ever wondered how we have like a 32-bit CPU? We have a 64-bit CPU, 32-bit memory, 64-bit memory, right? These are the things that have to do with the switches and how they're configured, right? Now, this is something that I'm going to share with you. And I want to walk through this with you because it's really important that you understand piece by piece what this little thing does here. This is the XOR, okay? And what we're going to do is kind of walk through this a minute at a time, a little bit at a time. So of the three basic logic gates, which one is present in the name XOR?
Or.
Is it and, or not? Obviously the or. Which one receives all of the other process? There's a lot of other process that happens here, but which one receives it at the end and does the final transition? It's the or, right? The X is significant because there's kind of a flip-flop here. The X, so what we have is a derivative. We have a creation that uses or, and the X is meaningful because there's kind of like a crisscross that's happening here. We have an A input. Walk through this with me, please. And maybe what we ought to do is just everybody stand up and shake out for 30 seconds, and then we're going to go 5 more minutes and we're done for today. Okay? We're done for today. So, I'll give you 30 seconds to stretch. And if you're in the room with me, I need you to get up and stretch. If you're not in the room with me, then you get to fake it. I want everybody to refocus before we go into the XOR. Everybody's seen the W before, right? W1, W2. You with me? Everybody's seen W1, W2. Yeah? No biggie. Everybody's seen knots before, yeah? Here's a knot. There's a knot. Okay? What we have are 2 ands. But when we feed A and B inputs, so how big is the truth table for this? How many inputs do we have overall? What does the input diagram show you, the big diagram?
2 inputs.
If you look at an XOR and you don't see any of the internal part, you only see 2 inputs. So how big is the truth table? Not trying to trick anybody here. What's 2 squared?
4.
It's 4. The truth table is 4 rows. That's it. That's all it is. 4-row truth table. Well, let's watch what happens. I have an A input, and whatever is fed into A is split into the top of and then it's fed down below, and it's fed into the top of the other and, but what happens first?
A. Flip.
It's flipped by the not. Does everybody see that? And instead of calling this W something, I've labeled this wire not A, because A is coming in, and then what comes out is something we call not A. Does that make sense?
Yeah.
That's A. Now let's look at the other side, B. Here's where we crisscross. And I want you to notice there's a split, but when you look at this diagram, and we got to zoom in really tight, right? Really, really tight. When you look at this diagram, what you see is a very small hump. What that means is that the wire runs under this wire, but it's not connected to that wire. This wire runs over the other wire. It's laid on top of the other wire. The little hump in the wire diagram is intentional. What it means is that this is connected, it's split, and those are fused. This is not. We have a wire that's insulated. It has plastic or rubber or something like that. An insulating material. Are you with me? The electric we just talked about, those wires are insulated. They're laid on top of each other, but they're not connected. So this B comes in, it splits, it goes up to the bottom end, and it runs across down to the lower end. It feeds the B input of the upper end and the lower end, except right here, what's going on right here. It's a crisscross. What's this and what is it doing? It's taking the value of the B and what's happening?
Flipping it.
It's flipping it. It's flipping it. So just like the A is flipped, the B is flipped. In this case, the A is flipped down here. In this case, the B is flipped up here. And you have like a crisscross. What you're looking at, ladies and gentlemen, is one of the things that makes the internet possible. What I'm telling you is that XOR has to do with network communications and encryption. And if we didn't have the XOR and we couldn't create an electronic component that worked like the XOR, we couldn't have encrypted fast network communications that you use all the time and you don't even realize it. You don't even think about it. This little bugger right here makes our entire internet connectivity. It's one of the things upon which our connected world hinges. This right here. And if you think about it, it's very understandable, isn't it? And or and not. It's just a crisscross kind of arrangement. And now you have a way to what? Open and close, switch, and if we add a little timing to it, that's all we need. If we add timing to it, now we have some of the basic functionality we need to build a computer. Without this piece, we don't have some of the very important things we need to build a computer. Okay. What I'd like to do is close our session out. I'd like you to watch for some basic assignments over the weekend. If you get a chance to complete them before the start of class on Monday, that'd be great. But you'll have until Wednesday of next week to get them done. So do them if you can. All right. All right, so that's all we had to share today. Thank you for joining us. And next Friday, we're actually going to be working with physical stuff. Okay, so we're going to ask you to come in and be here in person if you can. And we're going to be giving you physical stuff to noodle with. Kind of like science club back in elementary school. It'll be fun. Okay. I hope you have a great weekend. Any observations or comments before we close?